All right, recording's begun. And now I will turn off the chime. Gone. All right. Okay. And so, yeah, so, uh, it's a couple of points. One is Piazza's, there are great questions coming into Piazza and me and the TAs. And by the way, I just want to give them a shout out. These are some of the finest TAs I've worked with in a while who are it seems like doing a great job. I hope you agree with me. Of course, if you don't, drop me a private note, but I'll be shocked. But I need to know. So that's just in case. But at any rate, we are jumping on those as fast as we can and trying to get solid answers. And I just want to put out a request to, if at all possible, make your question a public question, because um, if there's some reason that we don't want to give everybody in the class the answer to your question, we'll take it private. But generally speaking, we want everybody to benefit from the Q&A that you guys do. So really, there's no reason to make your questions private. Unless there's a special reason to make your question private. So that's also okay. And then what I thought I would do, because there are still people who are still struggling with making multiple tasks run together. And we've presented a bunch of different scheduling concepts and all that. And I think some people have been a little overwhelmed by that. So I'm going to present an example and we're going to flash it into the Arduino and show you that this doesn't have to be that hard. And so I think I'm going to get right to that. I think I'm going to just go to the desktop and bring up this sketch. And okay, so here it is. And what we're going to do is just have two tasks. And by the way, as you create a method of scheduling tasks and running multiple tasks at the same time, definitely start that and test that with very simple tasks. And then you won't have the issue of a complicated task which has bugs in it breaking your schedule. You'll know that the tasks are simple enough and your scheduler algorithm can be tested without worrying about that extra complexity. Then you've got something that works like this. Go ahead and add more complexity to your tasks. Ideally, just a bit at a time, so you can see where things break. So what we're going to do, yeah, like I said, we're going to flash two LEDs. One of them will be the onboard built-in LED to save time, and the other one will be an external LED going through pin 10. Okay, and so what we have is some defines. So the internal LED. By the way, oh yeah, one other thing is I didn't play my background jazz this time because I think I figured out why my headset was dropping, which was in the old configuration, it used to be plugged into the same USB hub as the camera. And that was an embedded system issue where there's this high data rate going through the same hub from two devices, especially the camera, and there were just a glitch that would hang. And so far, when I was playing the jazz, I had the wireless unit for the headset plugged into either directly into the laptop or through a very lightly loaded hub, and it seems like it never happened. So definitely, though, I want to see hands up as soon as the audio dies, if it does die. But I don't expect it to die. All right, so internal LED is 13. That's just the way the board is wired. External LED, we're putting it in pin 10. And if you look those up in the schematic, that's port B bit 7 and port B bit 4. And then we're going to just, kind of write our code a little more generically. So we could port this code to another board by just changing the defines. That's the kind of the goal. And so we're going to say the LED port is port B, and the data direction register for the LEDs is DDRB. So those are the registers for port B, as you know. And the LED internal bit is bit 7, and the LED external bit is bit 4. All right. So then setup becomes really easy. And okay, I confess I did this example first using pin mode, but it's actually might be even easier to do the setup this way. And actually, oops, I forgot to use my pound define, so I'm going to do that. LED DDR. Okay, so we're going to set some bits for the two LEDs we want in the LEDs DDR. And all this stuff is defined right up here. And then that's all we need to do to set up our bits. We're not going to use the timer right now. Okay, now we're in our loop. And so this is, I don't even need this temp bit. I use that for some other example. So now we're going to have a loop, and it's going to have task A followed by task B, followed by a delay of 1 millisecond. And when we're running this, we're assuming that the tasks take 0 time. And we'll check that assumption in a little bit. But that has two consequences. One is, the main one is, it's on you to write your task so that it executes as close to 0 time as possible, but it's going to get called 1,000 times per second in this loop. So it can still get some work done. Although LED flashing is, I'm not sure I would define that as work. Okay, but it's getting something done. So now we have two methods or functions, task A and task B, which are obviously very, very similar. So task A, here's a key concept. We're going to have a static int in there. So what's the difference between an int with the scope of a function and a static int with the scope of a function? So they have the same scope, but static ints have a magic property which they persist from call to call. So if it's a regular int declaration, time will get reset to 0 and reinitialized, and actually it makes room for time on the stack. So the time variable will disappear after the task A function returns. But if we make it static, there's some permanent memory set aside for time, and it doesn't reset after each invocation or call to the function. We need that to keep track of time. And we know we're running once per millisecond. So if we just count the time, count the times that we get called, we have a measure of time in milliseconds. And so we can say if time equals 50 milliseconds, now the task we're going to have is 10 flashes per second of the LED, and you have to turn it on and off, and both the off and the on have to be visible to the human eye. So we're going to have it on for 50 milliseconds and off for 50 milliseconds. The total period is 100 milliseconds, which is 10 flashes per second. And so if time equals 50, we're going to set the bit in the LED port corresponding to the internal onboard LED. LED internal bit, which I defined up here. It's bit 4 because the, oh, I've got it backwards. What do you know? Okay. It always helps to walk through code, and professional places like Google, you will walk through your code with a couple of other programmers to catch stuff like this. So I made a little bug there. This is supposed to be the internal bit is 7. Oh no, I'm sorry. It's not wrong. external is 4, and we're supposed to do the internal bit, and the LI bit is 7. Okay, fair enough. It's fine. I thought it was working right. I have tested this. Okay, now we keep checking time, and because we're incrementing time whenever we're called, there has been an issue with on Piazza. Somebody used the millisecond function, which reports the number of milliseconds since you turned on the Arduino, and they discovered that it may skip a millisecond or two once in a while because something happened. And if that happens, this could be a bug, because what if it goes from 49 to 51? You'll never make this happen. This will never happen. Or even worse, from 99 to 101, and then we'll never reset time. So that's bad indentation there. Okay, you have to be cautious using equality and testing for equality. However, I know that I'm going to get to 50 because I'm incrementing time every time I'm called, and so it's a different way that time is counted here. Time could still be inaccurate, but I'm not going to miss time equals 50. Or I could just say, I don't want to say greater than equal to, because I don't want this to fire 50 times as we go from 50 to 100. So anyway, now we're turning on the LED. And then later on, or next, we check if time equals 100. If this fails, if it's 100, we turn off the LED. So we're ANDing with the negation of the bit, which we have to do to set a 0 in there. And we're setting time back to 0. So we start this over as this thing is repeatedly called. This thing, it's almost like it's in a loop. There's no loop in the code, but we know it's getting called 1,000 times per second, roughly. So that's kind of a mental adjustment to write your task that's going to happen a lot and does a little thing each time. Okay, and then we return. And then we have the same logical, it's really the same code. The only thing we've changed is the numbers and the bits. So for 1 time per second, we're going to wait 500 milliseconds and set the bit. And then at 1,000, we're going to clear the bit. And then we start over. But it's also called 1,000 times per second. And that's our operating system delta t, or our time quantum. So let's have a look. Let's see how this checks first for syntax. Okay, no red nasties. And then I have oops, I dropped you guys. I have my lab here, my lab bench, and I have an LED on the right, right there. I hope that's not blurry, but that's the LED. Ignore the 7 segment and ignore the 8x8 matrix, and we'll download. So I'm going to plug it into USB, and power lights up, so that's good. And then I'll do the usual. Oh, you can't see this because I'm of screen share. I apologize. Anyway, so there's my little setup, and I'm not using these big LED arrays, but I have a bit there, and it's actually running because I tested it before. So you can see the onboard LED is flashing about 10 times per second, and the external LED is 1 time per second. Questions, comments about this? I'm going to go back to screen share and go over the code. Why don't we use a global variable for time? Okay, I'll answer that question. It's a fine question. But I'm going to screen share first, back to the code. I guess I can do that. Okay. Um, so yeah. Why don't we use a global variable for time, and then we could increment it here? And in fact, that's a perfectly good thing we could do. There's generally a bias against globals um, in code. Um, People don't like them. This would be perhaps a justifiable exception because time is universal. We want everybody to have the same time. So we don't want any discrepancy between the times of the different tasks. So it's not a bad suggestion, but let's try it. So int time equals 0. What we might want to do is long int because these times that are in the tasks, which are independent of each other, they're separate memory. They just have the same name. Um, Remember, we're only going up to 100 here, and we're only going up to 1,000 for this one. That means to represent this time, 16 bits is great. 16 bits can go up to plus minus 32767. If we made it an unsigned int, we could go higher, okay? Because we're not doing any negative values. We can go twice as high to 65535. But now, if we're going to have a global time, we want to think about what happens when it rolls over. Because if it's an int, we only get 65 seconds worth of milliseconds before the time rolls over. And our tasks may not be smart enough to know what happens when you go from 65535 back to 0. So I'm going to make it a long int, which makes it much longer. And it's still an issue because you might want your Arduino embedded control system to run for many weeks, months, years. And so you have to actually pay attention to that. But we'll just address the issue a little bit by making it a long int. Actually, can be an unsigned long int, and then we get another factor of 2. So that's like a 32-bit integer going up to 2 to the 32nd. That's probably what Millis does, actually, because I think it was, what did you guys say? It's like 50 hours of running or something. So anyway, we got lots of bits for time. And then we're going to increment time in the loop. And now we've got a global for time. So now, but see, now I have to keep track of relative time versus that global. And so maybe it's a little more complicated because I can't reset it to 0. In fact, I think that's going to conclude my answer. So it's a very valid question. There might be ways you want to use it, but now my tasks have to store the time and look at the relative time from when they last reset themselves or something. And this is actually a little bit simpler to have a local clock that just goes back to 0 for the next cycle. So I'm going to just call this G time, and it's going to be unambiguous, our global time. And it can still be there counting, but it doesn't affect our tasks. And I'm going to download it. It just downloaded, and without moving the camera, I'll tell you the lights look just the same, but I didn't actually implement the global time. How does that for an answer to the question? Okay. All right, so I guess I just want to, I'll go back to that just to double down and share on the key take. Oh, no. There's one more thing, which I have another one. So this one, and I apologize, I did not get rid of the digital rights and pin modes on this one, but you see how to do that over there on the first one. This one, we're going to add another bit. And every time we go through the loop, we're going to set the bit or clear the bit. We're going to toggle it. And then we're going to use my handy little oscilloscope, which is optional. This is not required, but we're going to check if our assumption that the tasks take 0 time. So let's see what this looks like. So now we have this bit 12 is the loop bit, and we're going to make it an output. And our scheduler looks like this, or our basic loop. So we're going to have a little flag or integer called temp, and it's just it should be called flag or something like that. So then we call task A, we call task B, and we digital write temp to the loop bit. But temp starts to be 0, but then we have a little Boolean magic here with the exclusive OR operator. And so what this does, if the 1 bit of temp, if the bit 0 of temp is equal to 1, temp will clear it. This will clear it. And if bit 0 is equal to 0, then it will be set to 1. So you can think of the exclusive OR, which is that up arrow there, the bitwise exclusive OR, as a complement operator. It flips a bit. Whatever bit is on the right there will be flipped on the left. And so that means it's alternately going to write a 1 and a 0 to the loop bit, and we will then expect a 500 hertz wave, because there's one cycle where it's 1 and the next cycle it's 0. So that cuts the frequency in half from 1,000 hertz. And our expected frequency, based on the assumption, is 1,000. So I have my scope hooked up, and it's all connected already, and I'm going to set the values. I'll start with auto, but auto doesn't work when it's in 10x mode. Or maybe I have a bug, let's see. It's running too fast. Okay, so I don't have anything right now. And why is that? Oh, let's see. I know why. Because I'm running the old code. I'm not running this code. The old code doesn't have this loop bit. So let's check it. Let's upload it to the Arduino. Little lights flashing. And now, what do I have? There. Okay. So you can see that scope display. And I told you already that I didn't bother to calibrate my scope probe, so it doesn't look super rectangular, but that's just a matter of adjusting this little screw here, and I didn't bring a small screwdriver. Anyway, that is our waveform, and then there's a frequency measurement here, which is 488 hertz. So it's not really doing 500 hertz. Oh, again, I'm screen sharing, so you can't see. So we're going to stop the share. All right, this is better. So here is our waveform. And it is, as I said, it's not a perfect square rectangular wave, but that's the reason, is this calibration of the probe, and I can easily fix that with a tiny screwdriver. And then the frequency measurement is in the corner of the screen, and it's 488. 488, okay, that's sort of 500, but it isn't 500. And it shows you that, well, let's see, it's about within, it's certainly within 10% of 500, but it's not accurate. And that's, again, because these tasks do take some time. And so let's fix it. Let's tweak it. And so right now we're delaying now we have screen share so you can see this Arduino code. We have this delay of 1 millisecond, and that's too much. So we're going to get rid of that. And there is a routine in Arduino which delays by microseconds. And I fiddled around a little bit. And so we're going to delay, instead of 1000 microseconds, we're going to delay 985 microseconds. Basically, that's saying that task A and task B and this toggling thing together, they take about 15 microseconds. And then the total loop time will be 1000. So checking that, oops. I think that is an S actually. Yes, okay, I somehow deleted the S at the end of microseconds. So we're gonna upload this. It went in. Now it's flashing again. Now I'm gonna show you the oscilloscope. And now it says 498 Hertz. And I'm gonna tell you that's about as close as we're gonna get with this method. Sure, I could shave a couple of microseconds either way and get it to read 500. But the problem there would be then we're not robust to any code that has any different changes of that changes its execution time. Okay, any questions about this whole demo? No questions. Okay. Anyway, my point was to show that getting multiple tasks to work isn't that hard if everything's kind of simple, and if you mentally refactor. You're writing a task that is repeatedly called, and it spends just a little bit of time. All right. So now we're going to get back to some lecture on more advanced schedulers and also review. So again, I went through this before, and I think with this demo, it might be a little more, it might catch a little more for some of you because we just put it into action and we just modified it. So here is our very, very simple thing that more or less we just did, although we didn't put the delay. The delay is not shown here. And this is the key that made it work. That every task function is computing a little tiny bit and then returning, and that's just the generic template that a task has to follow. And if it ever starts to think and ponder and scratch its head and use up time, it'll break the whole schedule. And implicit in that is that the computing time is much less than the period, and the period equals our tick value, which is 1 millisecond. And that's kind of hardwired. You have to, the reason that more elaborate operating systems don't require you to code this way is because this is a little bit artificial. But tasks like these are totally doable if you program it this way. So now many of you have already set up the hardware clock, and you notice that the chip we're using has several, like 8 or 10 of these clocks, some 8-bit, some 16-bit. And so we could have a clock where it is set for 1 millisecond, and then we could write a function that watches it, watching the clock, like people in an office at 4:55 p.m. And it can watch the clock and then start the tasks and then watch the clock again. Or maybe it resets the clock, or maybe the clock is Okay, I'm back. Thank you for quickly raising hands. Um, I guess there's no actual questions, but I caught that. So, I wonder why when I'm listening to music in the background, it doesn't die. So my old explanation was wrong. Anyway, we caught it. So, um, as you saw before, for me to get close to 500 hertz, which was really 1,000 hertz, I had to fine tune that delay by hand. And that has obvious flaws, especially with code that might operate a little differently each time. So this is a way to get around that. This wait function will be looking at the timer in its hardware register and releasing itself or returning when the timer resets. So the same thing, same constraints on the compute time of the task and the period of the time of the task and the operating system tick. Okay, so first thing is, so we have this prototype of a function, and this obviously this requires all the programmers on the team to behave and write code that agrees with especially this constraint that compute time is much less than the period. It can't just be less than the period because you have to have multiple tasks. And so uh, if you want 3 tasks to run, you can't use even more than a third of the period for one task, etc. And so, then your system is only good as the worst programmer on your team or the person who's just beginning their project and hasn't fully debugged it or whatever. So this is artificial, and we can do it for these super simple tasks. But what about realistic tasks? So that's where preemption comes in. So preemption means the operating system forces a task to quit wherever it's at and break into the task and stop it. And we heard a little bit about this with interrupts. It can be done with interrupts. It is done with interrupts. So an interrupt occurs at a certain time determined by the scheduler, and the task is interrupted. Its state is saved though, so it can be restarted later. And now the state is restored from a different task, which is switched. Okay, and so I'm going to do a few more of these. We're getting to smooth them out, and we have some sort of more detailed examples here that I didn't do before. So I'll have the worksheet on my other computer again if it wakes up, and we're going to have a system interrupt every 1,000 microseconds now, every millisecond. We're going to mark those. And we're going to have these 3 tasks. So each exercise will have a characteristic set of tasks. And this is kind of like what we did before. Why is this not waking up? There. And we kind of got to this exercise too, different periods, the same compute resource for each one. The deadline equals the period. That's kind of what we did. Now here's a different one, sort of a heuristic or uh, sort of odd one. So we're going to kind of automatically give the the task A a different operating system period than task than B and C, and they have these specs. So now let me get this one going. And let me set it up to join the Zoom. Sorry, there's fighter jets flying overhead because that's what happens in San Diego. Okay, and I'm going to mute the speaker on this one. Okay, and share the screen. Okay, that worked. And so I guess I will, let me see if there's anything. Okay, chat, you lost audio. Got that fixed. Okay. And I'm going to pull up for my own reference those task parameters from the slide 37. And actually, I'll write them in here. So this is exercise exercise 3. Okay, leftover junk. Still got the bucket fill. Okay, and I'm gonna turn this around to make it a little better. And so task A is P equals 1 millisecond, and task B is, oh, wait a second. Oh yeah, but we have this unusual scheduler, this unusual code. I'm not going to write task. Oops, sorry. Wrong icon. Okay. Sorry, again, I forgot to put the wait function in there. All right. So I'm not going to write the semicolons. They're not coming out well with this pen. Okay, and so that's unusual, but it's just kind of a way to learn this notation. And so then our periods are 2, whoops, back to the pen. And task C is 2 milliseconds. And we'll put our interrupt ticks in there. I guess I could build those into the document, but it reduces flexibility. And so now let's run this schedule that's up here, which has this this unusual feature. All that's kind of a little different. So let's start with, and I guess I can get back to my filled rectangles. Oh, that's the wrong rectangle tool. That's a rectangle select. All right, got it. So task A runs for 200 these all run for 200 microseconds. So I'll put that rectangle in there like that. And then immediately we can run the second task. And then immediately we run the third task, about the same size, a little bit smaller than the blocks. And then we take up time we kill time until the next clock tick or interrupt. And these, since these have a different period, tasks B and C, we're, now wait a second, I want to make sure. Yeah, okay, good. Then we have a time delay for B and C. But we also have, after C, we're waiting for the next clock pulse, which occurs right here. And then we're going to quickly run A. So we didn't quite finish what we needed to do. Whoops, that's not right. It's after, yeah, it is right because we're synchronizing here. So this is the wait. Okay. And then after this, nobody's ready to run. We're waiting for the next clock pulse here. So that's going to happen right. We're going to go back to rectangles. Not sure this is the most ergonomic software. I don't know why that didn't fill. And this is the second wait. And now the loop goes back up to the top. So we'll just repeat this. Yeah, so now immediately we've done task A, B, and C. We're going to wait again. And that's the first wait. And then we can start A, B, and C again. Actually, no, we don't start B again because it's waiting for a second. It's asking for a longer period. But task A has finished a second time, so we have the second weight. And I think I'm going to stop fiddling around with all these all these fills and rectangles. Okay. Finally, we'll clear all this. And I haven't really explained or implemented yet a way to implement these delays shown by the green squiggly arrows. But we already talked a bit about like TCBs and how that we can keep track of a counter for each of those. Okay. This is a good time for our break. So we're going to take the 10-minute break and resume at 3:30. See you soon. Okay, welcome back. We'll just do one more. First of all, shout out to Seth. Seth, I mentioned the jets flying over, and Seth commented because he heard them too. I guess we're in the same neighborhood, so that's pretty funny. Um, and I guess I'll pause right now. Any questions? Did anything percolate through your brains during the break that you decide you'd like me to go over again? I see a hand, Lucas.
I would just have a quick question about because I realized that if we're using a static variable, for example, to keep track of our time, that means that with the exception of the scheduler itself, none of our tasks themselves can like call the delay function, right? Because that would just halt everything, right?
Exactly. That is a super key point. Okay. The way Arduino implements the delay function, I'm not actually sure, we can dig in and find their code, but it doesn't matter. The point is it blocks. And when you call delay 10 and you want to sit there for 10 milliseconds, that's fine, but you stopped everything else. So that's a key point. So I'm really glad you asked it. And that's why we're keeping track of time ourselves. And you'll notice that those functions always return right away, no matter what they're doing. They keep promptly returning, but they can still keep track of time. Anything else? Okay. Well, we're going to do one more diagram, slightly different, and address that because really your question also brings up a sort of another issue, which is, gosh, it seems like we're making every task keep track of time, and maybe we can abstract that so that we can have one code that keeps track of time and the tasks can use it. One, like for example, the delay function. Only we don't want that kind of delay function that blocks. We want a delay function which keeps the scheduler going for the other tasks which don't want to sleep, don't want to delay. And so let's do that. And we'll go over and share screen over here. Whoops. Zoom. Okay, Zoom, share. And we have a new fresh worksheet. And but before, and now that I've got that, that's good, but I'm going to go back to the notes, share on this computer. It's a little complicated, but bear with me. Okay, so we're going to do exercise 4, and we're gonna address this exact problem, which is suppose my task wants to sleep for 20 milliseconds and just wait. We can't use delay, um, and so we want to return to the scheduler. We're going to use a software counter to keep track of that delay, and then um, every so often, and then when the delay gets to 0, we'll start you up again. And so let's work on that, assuming that we have a sleep function. Sleep is not the same as delay. So sleep says, put me to sleep for 25 milliseconds, but keep everybody else running if they want to. And so we're just going to assume the existence of this. And we've already talked a little bit about how those work. And now our 3 tasks are going to be the following. The first one's a period of 2 milliseconds, and it computes for 233, just another one of those slivers. This deadline is 1 millisecond after it starts. So every 2 milliseconds, it has to be done within 1 millisecond, if that makes sense. And task B is a little slower. So it's got a 4 millisecond period and similar compute and similar deadline. So task B is going to look like this. It's going to be compute for 233 microseconds, more or less, sleep for 3 milliseconds, and return and start over. So this is easier for the programmer to write, right? It's kind of like being back in high school writing an Arduino task using the delay functions, because you just sleep for however long time you want, but you're not breaking the other tasks this way. And then C is one of our hardcore hard real-time tasks that runs every millisecond and computes for 1/10 of a millisecond. And so we'll do those. So now I'm going to stop sharing, but keep that up on my screen on the right so I can sort of label them, and then get back to screen share on this computer. All right. And so this is example 4, pen, no fancy rectangles, and red. Uh, 41 or 40, let's call it. And right, so A has a period of 2 and C of 233. And B has a period of 4 and a C of 233. And C is our hardcore one. Better run every time. But it's fast. Okay. And I guess, and this one has, yeah, okay. And we assume the sleep function exists. So let's just start diagramming. Okay, now I've got a good screen set up. And oh, we'll put our interrupts in, sorry. And now we'll get to fancy rectangle mode. No LaTeX, please. Oh gosh, what happened? Good, okay, no problem. Cancel, all right. Great, all right, so A starts for 233, which is sort of this much of a bar. And then C was going to generate about the same compute. And task C is very skinny, 1/3 of a bar. And then our scheduler will synchronize somehow. We're assuming that. So it will take over. And we'll label that later so I can keep with the rectangular tool. And then we'll start this again, except A is not ready. It has a period of 2, so it's doing a sleep of 1. So A is not ready. B is not ready either because it's got a period of 4. So it's doing its sleep for 3 cycles. But C is ready. So C is going to do its little thing right here, whatever that is. And now no tasks are ready. So we're going to just burn all the time available, watching a timer or waiting for an interrupt or something. And then it's the next tick. So now A is eligible to run, but B isn't. B is trying to delay for 4, I'm going to start, I'll clear my rectangle and bucket fill and start putting in time delays. So this is going to skip 1 and go to the second clock cycle. This is a delay of, this is a sleep. I didn't explicitly show that in the task descriptions, but that's how you would implement the period of 2. And similarly, P is going to have a very big green squiggly arrow. 1, 2, 3, all the way down to here. 1, 2, 3. Actually, it's going to be here. Okay, so this is where there's going to be some quantization, potentially quantization error. So if we really want to, well, let's see what happens. We said it was a delay of 3. I mean, a sleep of 3. So we're going to take it the way it's supposed to be. So we're sleeping through 1 tick, 2 ticks, and 3 ticks, and then we're eligible for the 4th. Then we go to 0. I guess it's the exact implementation of how you do that could be that it ends here, or it could end here. So let's assume that it ends n+1 ticks later, and that will solve our dilemma. And then, of course, this one doesn't have a squiggly line because it's just running every time. It's not calling a delay. So anyway, getting back to task graphs. So task B is not eligible, but task C certainly is, and it's waiting its turn. And because it's later in the alphabet, it doesn't get to run right at the millisecond boundary, but it's within its deadline. And now, oh, and going back to this, we've now sleep 1 again. So we go past 1 tick in order to get a period of 2. So, okay, nothing's eligible after C runs. So the operating system or scheduler has to burn all of that time. And then at this next stage, again, only C is eligible. And now we have time to burn because nothing's eligible yet. And now we're kind of at a common divisor of all the periods. And so now we're going to start the whole process over just like here because everything's eligible to run now. So I don't know, seems like I'm getting less confused about the rectangles and bucket fills right now. So I'll go with it. So we have A, just like the very beginning, B, and C, skinnier. And it starts over. It repeats. Okay, so again, just reviewing, maybe I can zoom out a little bit. Yeah, I can. Okay, sort of the big picture is that we follow the sleep commands or sleep calls of the different tasks, and then they get to pick their own period as long as the period is a multiple of the operating system tick. And what you find in many practical systems, and again, these are not widely, available. They're not like typical codes you find on the internet because when somebody's programming an electronic braking system or a home security controller or a medical device or any of these things that embedded systems are for, they're just not posting their code on the internet in general. But my point is this, that in real applications, yeah, maybe there's some things that are really intensive real-time tasks like task C, which are really needed to run every operating system time tick. But more commonly, tasks run in this mode where their period for the task is multiple time ticks, even dozens or 20 or something. For example, if I want to control some kind of motor, it may be perfectly acceptable to control it 50 times per second. And 50 times per second means that I can have 20 milliseconds of, is that right? Yeah, it is. 20 milliseconds delay between updates between calls. So my controller for that motor might run a little control and then sleep for 20 milliseconds. And that's a low ratio, but that's sort of a very common mode that real-time operating systems are used in. And most real-time programmers would get very nervous if you had lots of tasks running at whose period is equal to the operating system tick. And these examples that I'm graphing are nice because they're unusually nice because the compute load is constant all the time. But real tasks, it can vary. And so what people are obsessed with in real-time systems is, can the schedule be completed so that every task meets its specifications for CP and D, compute, period, and deadline. And you could easily imagine a case where we just jam a little bit too much in here and it's not possible for all the tasks to run. And since tasks sometimes take longer and shorter, it's very dangerous to crowd this schedule too much. So we'll talk more about that, but I think I'm going to wind it up for today. I hope this has been, especially the initial part, has been helpful for your labs. Keep the questions flowing on Piazza. We will stay on top of them. And again, reminder, think about putting your question as a public question. There's no shame. All these are good questions. I really haven't seen dumb questions, honestly, even the private ones. And so I just assume that everyone gets the benefit of those questions. So I'll wind it up there, but I'll stay on for Q&A or discussion. But you're now free to sign off. I think I'll stop the recording. Actually, I may leave it on in case there's interesting questions. So I'll stop this from screen share. And I'll throw it open.
Thank you, Professor.
You are welcome.
Yeah, hello, Professor. I was just wondering if you could do like because I think the LED matrix I have is the raw 16-pin one, and I've read the lab book. I've looked over the internet, and I think it would be nice if exactly like how you explained the scheduling part in the beginning of the class. I think it would be nice if we I guess for you to, I guess, explain a bit on how to deal with that particularly, because it's okay. I'm not exactly sure how to say this, but the diagrams and like the pins, I don't find them like 100% intuitive, because you know the pins are on either sides of the board, and it's I played around with it a bit, and it's I'm currently, I haven't found like a pattern of how things work here. I just know that some has to be high, some has to be low in order for one specific light to turn on. So I think we'll be pretty
Do you have the
constructive.
schematic for your specific LED array?
I believe I do. It's 158 BS, right? 1588 BS. Is it
Sounds right. I mean, there every single digit matters in there.
right?
You know, the BA versus the BS, they're going to change the pin out. It's 100% intuitive is a very high bar.
Right.
But
Yeah.
do you want to screen share your schematic?
So I mean, I just went on the internet and I looked at the first one I found, and it's. I mean, I guess one of the things is for all of the. Give me 1 second, please. No. For. Ooh, okay. So for let me do some minimizing in 1 second. I mean, for all of these schematics, I think it's a bit. Okay, let me just get this on and. Okay. Because all of the schematics, like even the ones for the 1088,
Yeah, this is great.
yeah, it's so because the pin, at least for mine, is there's a row of 8 pins on the side where the model name is, and then another row of 8 pins on the opposite side.
Yeah.
And so I'm not sure where the pins are in this particular schematic. Yeah, like I understand it's supposed to be wired up like this. I mean, I didn't use a breadboard. I just wired up all 16 pins directly to the Arduino. And I'm trying.
Yeah, let me talk you through it. Okay, so start with the top. So the photo on the top. So you've got the pins labeled there.
Yeah.
You've got the hopefully the number is printed on the side of your actual unit. Is that correct?
Yes, that is correct.
Great.
Exactly like that. Yep.
Great. And let me just, out of curiosity, what do I have? Hey, out of curiosity, I have the same one. So that's kind of cool. By the way, I meant to castigate the class a little bit. There's a video that we refer to in that lab that shows the proper function of the LED matrix, and it only has 12 views on YouTube, which means most of the class hasn't even looked at it yet. And so definitely watch the video to see what your output should look like. But first you got to get the pin out. So now you see 1 through 8 and 9 through 16. And of course, they're not really visible there, but that's showing you where the pins are, hopefully correct with respect to the lettering on your device, right? And then you've got the pins, now the middle, before we get to the matrix there, the middle, now you've got pins 1 through 8 on the bottom row and 9 through 16 on the top row. No, the middle, the pin out, the thing that's labeled pin out.
Right. So this bottom 8 is corresponding to these 8, and the top 8 is corresponding to the other side. Okay.
And as you know, they aren't like right at the edge of the device. They're kind of internal. Yeah, and which makes the wiring a little painful. But now you see row numbers and letters applied to those pins. So for example, now let's say you wanted to try to light up the upper left-hand corner in the thing called diagram. You're pointing to it. That's right. So now you've got to make pin 8, the pin called 8, which is row 8, high, and you've got to make the A column low. And this is a very confusing and complicated pinout. I feel your pain, but it's readable. So we look for row 8. 8 turns out to be where is 8?
That's a good question. Wait. Is this no, that's 2. Wait, oh no.
Hold on, don't move it. I'm still understanding that. We've got A, B, C, E, D, E, F. So we G and H. So we got all the columns present. And then in terms of numbers, we got 0, 1,
It looks like
2, 3, 4, 5, 6, 7, and not 8. So those are 0-based row numbers.
So 7, this one right here is 8.
Yeah. So, well, no, there's, so the pin number there would be 1, 2, 3, 4, 5 would be row 7, which their diagram incorrectly labels 8. Which is, this is horrible documentation, but sometimes we just have to deal with that. Also, if you keep searching, I think you can find a clearer pinout for this device, because I found one that was better and not as confusing as this one for the same device. In fact, isn't that in the lab write-up? Because you and I have the same device.
The lab write-up. Let me take a look at that. Okay, so I guess one more thing actually is so from our understanding, then so if we make 8 high and then A low, that means it's gonna flow in from 8 through the diode and then out into A, and that will light it up, right?
Correct.
Okay.
And you can use your DMM, and I suggest you really do that to check this, and make sure you've got the pinout understood properly. But you're in luck because your device is exactly the same as my device. And so what I wrote up in the lab write-up applies to you.
I'm just taking a very quick look. Where's the lab? My lab is
Why don't you share it?
Yeah, give me 1 second, please. Lab 2, official version, number 4. Consult this. Give me 1. Okay, there we go. Let me drag this out. Its own window, and let's take a look. Share screen. There we go. So raw 8x8.
Yeah.
Right. I mean, in the case of mine, it should be.
Well, just read the figure legend. So the right. Wait, go down. Don't stay there. So show the 2 diagrams.
Yeah.
Okay. Though it says on the right is type 1088BS.
So on the left, yeah.
That's interesting because the one on the left looks like your diagram, but I couldn't get it to work until I had I use common anode on the right.
So let me take a look at the one that I found on the other website. It looks like, let's see. So it goes from horizontal to vertical. Yeah, the one on the left appears to be the 1588.
Oh, you have 1588. Okay.
Yeah. Yes.
I'm sorry. I have 1088BS. So there you go. But anyway, here's the thing. Figure out, if you can, the pinout, and then use your DMM to test it in diode mode. So the red lead is positive, the black lead is negative, and touch the pins and see if you can make it. Your DMM should make the pin light, the LED light up.
So then the logic behind this is whenever I need to turn anything on, I I keep its row on high. Oh wait, like yeah, I keep the
Yes.
row that it is on high, and I keep the column that it is on low, and then that's gonna turn only that one on, right?
Exactly. And all the other columns are high. And
Okay.
if you send all the, you can light more than one at a time. If you in a given row, you can light more than one if you lower more than one row. But the assignment only requires you to lower one row.
I see. Okay, yeah, that's making a lot more sense now.
Excellent.
Okay, great. Okay, yeah, thank you very much.
And don't forget to watch the video that's linked into the document, and you'll see how it works.
The video actually, where's the video? What page is it on again? Because I think, oh, I found it.
Yeah,
Is it last? Is this page 7?
it's just a YouTube. You can't
Let's see.
not see it.
Okay.
And I only 12 people have watched it. It's only got 12 views, and I've watched it a couple times. So I'm gonna. I forgot I was going to mention it in class that people need to watch that, because then you can see what it's supposed to do.
Yeah. Okay. Yeah, I think I probably missed that. Yeah, I think I did miss that. I think Ishan's cursor is on it right now. All right, makes sense. Okay. Yeah. Yeah. Thank you very much.
All right, good. Good luck with the lab.
Okay. Have a great day.
Other things, other questions?
I didn't message you a question. I'm not sure if you saw it. Basically, I was confused in the first example, the coding example from class today. You had a scheduler that used like delay of 1 to synchronize the loop. But you also said that that's not completely accurate. So I wasn't sure if is that a valid way to do it for our lab to be more accurate?
Yes, because you don't have an oscilloscope. I mean, obviously, I encourage you to get one of these if you can for $75. It's kind of incredible that you can get this for $75, but that is definitely not a requirement. And so, if you're accurate, if your accuracy is similar to that, 488 versus 500, and basically the only way we're going to tell on the video demo that you submit, we're going to tell that by the sound, and does the pitch sound right? And none of us are perfect pitch trained musicians that are going to be able to resolve that frequency to 2 hertz or something. So if it sounds crazy wrong, then it's not just a little bit off. Does that make sense?
Yeah. So the scheduler that you, or the scheduler format you used in the first example, that would be a valid way to do it in our code.
Yeah. You mean the Arduino?
Yeah.
Mm-hmm. Yeah.
Okay. Thank you.
There's a question in the chat. I guess I just answered that question. So yeah, that's acceptable accuracy for lab 2.
I have a more general question about scheduling.
Okay, sure.
So in the scheduler that you mentioned, so we're doing round robin scheduling from what I remember. And so it's like we break up whatever task we have, like in the code demo that you showed at the beginning of class, we break up whatever code we want to do into very small bits.
Yes.
Yeah. So is that the case for all schedulers? It's like taking whatever we want to do.
So I've
Okay.
briefly introduced, but we haven't done anything yet in detail with preemptive scheduling.
Mm-hmm.
So your laptop that you're using right now is running preemptive scheduling, which means the programmers of Zoom and all your apps are just writing code for their apps. And the scheduler is just stopping them by interrupting them and switching in other tasks to make it seem like your computer is running all these things simultaneously. but you have a scheduler in Windows, Mac, Linux. They all have schedulers, and but in a heavy duty, full size system, it's preemptive. So the programmer doesn't have to worry about being nice to the scheduler. The scheduler just stops it and switches something else on.
Okay. Okay, cool. Thank you. I was a little confused because when I was doing lab 2, I was thinking like I want to do like all of task A and all of task B. And like how do I try to mesh them together?
I know.
And then,
And honestly, it's been a long time since I've taught this course, but I've taught it many times.
Mhm.
And I just remember this is one of the things that's hard for students and anyone to change their thinking, right? So
Yeah.
you just refactor and think and try to write your code a totally different way so that it can just get little bits of the task done and return. And it
Okay.
has to trust the scheduler to keep calling it over and over. Otherwise it won't ever get done.
Okay. Okay, cool. Thank you for the explanation.
All right. Good question.
Okay.
2 people left. Any others?
I just wanted to talk about something interesting I found. I was the one
Sure.
who posted on Piazza about the millisecond skipping thing.
Mm-hmm.
And when I was testing more of like with my initial like implementation, I found that if I set the OCR4A to different frequencies, like setting it up or down like 500 to 40, it skips at different times. So let's say I set it to 60, it skips maybe the 4th loop or the 5th loop. And then when I set it to like 500, it skips only like the 31st loop and very infrequently. So I found that pretty interesting.
So you're saying that you were changing hardware timer 4 and it was messing with the millisecond thing that came back. Is that correct?
I believe so.
Okay.
In some sort of way. Because that's the only way I could understand, because for some reason, higher frequencies would skip a lot more than what lower frequency at a certain point, but it would still skip once or twice, but very infrequently.
I'm really surprised and unsure why that would be. And the reason is because I would think that if milli is using timer 4 at all, then our project is just going to smash it into pieces, and it's it's not going to be a subtle error like dropping a millisecond here and there, right?
Mm-hmm.
And so the other explanation could be if the timer is generating interrupts that interfere with some other interrupts that are helping Arduino do the millisecond function. That might explain it, but we're definitely clearing interrupts. At least you're supposed to be clearing or disabling interrupts on timer 4 in the initialization according to the lab write-up. So assuming you did that, that means that the timer 4 is not generating any interrupts, and so that explanation doesn't apply either. So I have to say I'm kind of baffled about that. And what we could do is dig into the Arduino code base and look at everything they do, but I just don't have time to do that this quarter. You could do it if you're curious. If you want, engage with the TA Brody, because Brody has dug into some of these things, and he has some. He's installed some other software which makes it very easy to click through to the Arduino functions. If you're using the Arduino IDE, as I am, you have to go search for those functions in complicated directories, but Brody has it set up that he can just like click on the code and it will open up the Arduino function. And so you guys together could track it down, and I'd give you 5 extra credit points if you briefly write that up. But it'll be faster if you work with Brody, because he's got that sort of down.
Yeah, I just found it pretty interesting because because I
It
tested
is
quite a
interesting.
bit.
And it's disturbing because it's a semi-subtle effect. And I also, the fundamental problem is that Arduino uses some timers, and I don't know exactly which they use. And I tried timer 4 and I got away with it. Okay. But I'm not absolutely positive that there are no circumstances where Arduino is trying to use timer 4.
Well, thank you very much, Professor.
You're welcome. Good comment.
Thank you. Have a nice day.
Thank you, Sunny. Any other comments, feedback? Okay, I guess class is over. I'm going to stop recording.